Okay, please let me know when you're able to see my screen.
Yes, sir.
Okay, great. So we were talking about in the previous class, we had started this lesson on complex integration. So I introduced the idea of a complex line integral. Okay, so this is how a complex line integral looks like. You need an integrand, which is a function. Okay, and you have a curve C. That curve is the path of integration. This function f of z that we have, there is no requirement that it has to be analytic. Okay, so analyticity actually helps us, okay, to easily evaluate this function, as we will see from the Cauchy integral theorem. Okay, from there we will see how analyticity actually helps us to easily evaluate this. So now this curve C may have a parameterized representation. That means we could represent this in terms of some parameter t. This need not be just t. You could just call this parameter some other value also, some other real number. Let's say theta also you could have it. Okay, so this was the sense of positive sense of the curve is the direction of increasing t. So that direction in which t increases, okay, that is the that is considered to be the positive direction of c. Okay, so now what we do is we partition this into lots of many intervals. Okay, so each of these intervals we have samples, that is t naught to tn. Okay, for each of these t naught to tn, we have individual points on the complex plane z naught, z1, and so on, all the way till zn. So this is the parameter for each of these. We have individual points on the complex plane. Now, because there is a mapping, there is a function here. So for each of these z points, we'll have a in another complex plane, we will have the value of the function. So z naught will give us f of z naught, z1 will give us f of z1, and so on. Okay, so that's why if you change this parameter, you are actually changing the values of the function as well. Okay, so now suppose we take any of these two, any such interval, okay, sub interval along this segment. Then within this interval, we define a new variable zeta k. Okay, and the separation between them is delta zk, and then we form this kind of a sum. So how you get this sum is the value of the function as this zeta k, multiply this with delta zk. Okay, and then you add up over all of these segments. That is going to give us the sum, and in this sum, as n tends towards infinity, that limit, okay, that limit becomes the line integral, the complex line integral. So this is the definition of the complex line integral in terms of a infinite sum. So what we do is next is we write down, because this is a complex function f, we write down this function as u plus iv. Again, once again, note, I did not mention anything about any relationship between u and v. In other words, I did not say that the Cauchy-Riemann conditions hold good, so f need not be analytic. Then because this zeta is a complex number, it can be written in terms of a real part and an imaginary part, and this delta zk also will have a real part and an imaginary part. So putting all of these in, okay, and when you take the limit, okay, so putting all of these in, that we have four summations now. Now when you take the limit of this, you will get the line integral. So that means if the function can be written as u and v, okay, in terms of u and v, you can evaluate the function this way as you take the limit as n tends towards infinity. Okay, so now this is, I think this is where we had stopped, no, in the previous class. So next we'll look at some of the properties of the complex line integral. The first property is linearity. Okay, so linearity, it means exactly the same as you are already familiar with. So linearity means, so suppose I have two functions, okay, f1 and f2. Okay, I am having two functions f1 and f2. The first function I'm multiplying with some constant k1. The second function I'm multiplying with some constant k2, and I add both of them together. So this is a linear combination. Okay, so when I say a linear combination of f1 and f2, a linear combination, a linear combination of f1 and f2. Linear combination of f1 and f2 is some constant k1 into f1 plus some other constant k2 into f2. This is, let's say, some function f of z. So then, because this f of z is a function, I have two functions f1 and f2, and these two functions I have formed a linear combination. The linear combination is also a function. That function can be integrated. You can find out the line integral. So this line integral will be simply k1 goes outside, line integral of f1 plus k2 times the line integral of f2. So that's the linearity property. Next, we have the sense reversal property. Sense reversal property is, so suppose I'm trying to integrate over this curve. Okay, let's say I have a curve. Okay, the starting point is z naught. The starting point is z naught, and the end point is capital Z. And then I want to integrate along the direction which goes from plus z naught to capital Z. So let's say I want to integrate in this direction. So along this direction, if I integrate, I will get some integration. Okay, some integral value. Okay, the integration of f from z naught to capital Z. Okay, this is going to give me some integration value I. But if I integrate in the other direction, the opposite direction, then this integration, the integration from z to z naught of the same function, this will give me minus I. So the integration you get, the line integral that you get in one direction along the same path, okay, not along a different path, along the same path you go and you integrate, and then you come back in the opposite direction. The integrate that you the value that you get, the integral that you get in one direction and the other direction, they will be inverse of each other. So there will be a minus sign which will be included. So whenever you have a sense reversal, you have to include a minus sign as well. Next property is the partitioning of the path. Partitioning of the path, again, very straightforward. So suppose I have a path, a total path that looks like this. Okay, so this is the total path. This is the total path C. I want to find out the integration over C of some function f of z. What I can do is I could divide this path into many small parts. So I could say from here, this part I could call it as C1, this part I could call it as C2, this part I could call it as C3. So this integral, okay, integration along this path is the same as integration along C1 plus integration along C2 plus integration along C3. Okay, so that is known as partitioning of paths. So linearity, sense reversal, and partitioning of paths. So these are three properties of a complex line integral. Then there is a theorem. Okay, the theorem, it helps us to evaluate the for analytic functions. It helps us to evaluate the integration. Okay, it helps us to evaluate an integral, a definite integral. So let us say, let f of z be analytic. So suppose I have f of z, this f of z. Let us say it is analytic. Okay, in a simply connected domain. Does anybody know what's a simply connected domain? What is a simply connected domain? Any idea? What is the meaning of a simply connected domain? Domain. What is a domain? Domain is a collection of, it's basically a set. No. So suppose I have a real. This is a real axis. This is the imaginary axis. Then I could say that the function is defined over these values. Okay, the function is defined over these set of values of z. Okay, so that is the domain. That's the domain. Simply connected means this domain does not have any holes. Okay, if this domain has got holes like this, that is in between domains. So suppose we have some gaps in this domain. That is, the function is defined at all points except all the points in the shaded part. The function is defined at all points in this shaded region. Okay, in this shaded region, each and every point in the shaded region. So these holes that I have drawn over here, the function is not defined in this. So such a domain is not a simply connected domain. It's a multiply connected domain. Okay, so this is not simply connected. This is not a simply connected domain. Okay, it will be simply connected domain only if it has got, there are no holes. Or in other words, if a domain has got only one boundary, then that's a simply connected domain. Okay, a simply connected domain is a domain which has got only one boundary. If it is, you just count the number of boundaries. So what kind of domain is this? It's a triply connected domain. It's a triply connected domain because there are three boundaries. This is one boundary, this is another boundary, and this is one more boundary. Just count the number of boundaries. So here there are three boundaries, so it's a triply connected domain. Okay, or threefold connected domain. Okay, so this is the meaning of saying that there is a simply connected domain. Okay. All right, coming back to this. So suppose I have a simply connected domain and a function is analytic and it is defined on a simply connected domain. Okay, then there exists an indefinite integral. There exists an indefinite integral of the function in D. Okay, there is another analytic function. So the indefinite integral of small f is another function, capital F. Okay, so what I mean by that is this. So small f of z, okay, is the function that I have at hand. Associated with the small f of z, there is another function, capital F of z. Okay, this capital F of z is the indefinite integral, of f of z. Okay, so as an example, so let us say f of z is equal to z square. Okay, if f of z is equal to z square, then what is capital F of z? Capital F of z will be the indefinite integral. So what is the indefinite integral of z square? The indefinite integral of z square is z cube by 3. So z cube by 3 is the indefinite integral of this one. Understood? The same rules of integration. Integration of x to the power n is x to the power n plus 1 divided by n plus 1. The same thing. Just replace x with z. So z to the power 2, the integration is z cube by 3. So this becomes the indefinite integral of small f. So small f will give us a capital F. Okay. So this is the indefinite integral. Okay. So and this indefinite integral is another analytic function. Okay. This indefinite integral is analytic function. Okay. Such that the differentiation of f of z is going to give us small f, because you can see here, if you differentiate, what you will get if you differentiate z cube by 3, we'll get 3z square by 3. 3 and 3 will get cancelled, we'll get z square. Okay, so that's the idea. The definition of an indefinite integral is we are looking for a function which, when you differentiate, you get back the original function. So original function is z square. So you have to ask yourself, what is that other function which, when I differentiate, will give me z square? The other function happens to be z cube by 3. That z cube by 3, when you differentiate, you will get z square. Then z cube by 3 is the indefinite integral of z square. Okay, and this is also analytic. Okay, so suppose I have small f, which is a analytic function. Then there is another analytic function whose derivative is small f. Then for all paths, this is not for form, this is for all. Okay, this m, that's a typo. Okay, that's a typo. There's no m. So for all paths in D joining 2 points z1 and z0 and z1 in D. So what we mean by that is this. So let's say this is some domain. Okay, this is some domain. Okay, let's say this is some domain. This is some domain, capital D. And in this domain, let's say we have 2 points, z0 and z1. Now the function f of z, is analytic. The function f of z is analytic. So which means this is analytic. That means this is going to have a indefinite integral, capital F of z, such that if you differentiate this, you'll get this. Okay, if you differentiate this function, you'll get this. Then for all paths, so whether you take this path, you take this path, okay, or you take this path, or you take any other path, okay, between these 2 points, whether you take path C1 or C2 or C3, any path, the integration, okay, the integration over path C1 is the same as the integration over path C2 is the same as the integration over path C3. So it really does not matter which path you are integrating. All that matters is that the two endpoints, that's all that matters. The two endpoints Z0 and Z1. The two endpoints Z0 and Z1. That's all that matters over here. Okay, and this result will be, you take the analytic function, the indefinite integral, substitute the upper limit and minus the same analytic function, so same indefinite integral and the lower limit. Okay, so that is going to be the evaluation of this analytic function from one point to another point if you know the two endpoints. So this seems very familiar to you because this is something that you all have been doing since your school days, right? For real functions, that's how you had integrated. So the same thing holds good here also. So now suppose I ask you to evaluate this. How do we do this? By using this. How do we evaluate this? We can just use this directly. Okay, so in this case, what is z naught? Z naught is 0. And what is z1? Z1 is 1 plus I. Okay, so I need to find out what is integration from 0 to, that is from z naught to z1 of z square into dz. We need to find out this, and according to this theorem, this is equal to the value of the function at z1 minus the value of the function at z0. Okay, so now if you can find out this capital F, then the problem is solved. So here what is small f? Small f in this case is this. Small f is z square. If small f is z square, then what is capital F? Anyone? Capital F will be simply z cube by 3, as I showed some time back. Okay, so capital F will be z cube by 3. So therefore the value of this integral is going to be, just substitute wherever z1 and z0. So that is z1 cube by 3 minus z0 cube by 3. Okay, so it is 1 by 3. Okay, z1 is 1 plus I whole cube minus z naught, which is 0 cube, which is 0 itself. So can anyone calculate this, evaluate this and tell me? Just evaluate this. 1 plus I, a plus b whole cube formula. Use the a plus b whole cube formula and use this, I cube is equal to minus, I cube is equal to minus I, and I square is equal to minus 1. I square is minus 1 and I cube is minus I. So use that to evaluate this. So somebody please do that. Not somebody, everybody, all of you please do that. Evaluate this.
Sir, minus twice I by 3.
Who said that? Who's this? Who's going to give this answer?
Sir, Korobi.
Korabi. Can you tell the answer again? Minus?
Twice I by 3.
Twice I by 3. I hope everybody got this answer. Others, please just check. Minus 2I by 3. One plus I whole cube. So 1 cube plus 3 into 1 square into I plus 3 into 1 into I square.
No, sir, I have done it wrong.
Yes, that's why there should be two terms, no? So we will get 1, then we will get 3I, okay, then I square, that is going to give us a minus 1, so minus 3, then this I cube is minus
minus 2I.
yes, good, because 3, yeah, 1 minus 3 will give us a minus 2, and plus, no, plus 3i minus I plus 2i, no.
Plus 2i, sir. Plus 2i.
Yes, yes, this is not correct. So this will be equal to minus 2 by 3 minus 2 by 3 1 plus I. Okay, so I hope you got this answer. Everybody, did you get this? Same answer. Minus 2 by 3 1 plus I. Sorry, no, 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 it should be minus 1 minus I. It should be 1 minus I. Korabi, did you get it?
Yes, sir.
Okay, great. So we have some more problems. Please try them. Please try them. Okay. Let's do it now itself. Okay, because now we can do that right now. So two, number two. Can you try number two, all of you? I guess you'll have to use for number two. You have to use those relations which I had given in the first class. Some basic trigonometric relations for complex numbers. Not those things you have to use here. Yeah, I think we can do it. You can do it at home only. Okay, please try these. Okay, the remaining three, you just try them at home. So we'll now go to the next one. Okay, so now this is, you can directly integrate. You can directly integrate a function. Okay, you can directly integrate the function. But what if the function is parameterized? Okay, what if the function is parameterized? So let's say f of z is a piecewise smooth path, and it is represented by z equal to z of t. That means there is some parameter. T is a real number. T is a real number, and as this t changes, z also changes. Okay, so z is parameterized by t. So in that case, I want to find out the line integral. Then what I can do is, in that function you replace wherever there is z, you replace that with z as a function of t or whatever is a parameter, multiply that with the derivative of z, and then integrate this with respect to the parameter. So if you do that, that is going to give us the result that we are looking for. Okay, so let us just do one problem. Okay, so these are the steps. Represent the part C in the form of z of t over 0 a less than equal to t less than equal to b. Then you calculate the derivative. Whatever is a z, z is a function of t already you have. You differentiate this. Okay. Then wherever there is z in the function, you replace that with z of t. That is, write everything in terms of the parameter. Then you integrate that function with the z replaced with the parameter multiplied with the derivative of z, and you integrate this from a to b. So let's do this problem, the first one. Okay, evaluate z to the power n, z to the power n over a path. The path is a circle. The path is a circle of radius rho in an anti-clockwise direction, and n here is an integer. Okay, let me do this problem here properly. Just a second. I just grabbed this the text of this problem. Okay, so this is the problem that we'd like to solve over here. So how do we go about solving this? So here the parameter that we choose, oops, here we choose the parameter. We choose the parameter as this t, we choose it as theta, and theta you already know, theta is the angle, no? So we have, let's say this is a complex plane, this is a complex plane. So let's say this is a complex number z. So what is theta? Theta is this angle, that angle that it makes with respect to the real axis, the angle that the complex number makes with the real axis. So that is the theta. So we choose theta as the parameter. Okay, so now the question is, why did we choose theta as the parameter? The choice of the parameter depends on the kind of paths that you have. And what kind of paths do we have here? We have chosen a circular path, right? We have chosen a circular path. So because we have chosen a circular path, that means the radius does not change. Okay, we have chosen a circular path. Okay, we have chosen a circular path, and because we have chosen a circular path, we know that it's the radius along this path. The radius is not going to change. So let's say this is a circular path. Okay, so as you move along this path, okay, as you move along this path, so let's say I take some point. Okay, I take some point z, and I'm moving along this path in the anti-clockwise direction. So this is a complex number, and I am moving in this in the anti-clockwise direction. That is, sorry, I'm moving in the anti-clockwise direction. So as I move in the anti-clockwise direction, what will happen? We realize that this theta is going to increase, right? So anti-clockwise direction is a direction in which the which is taken as a positive direction. Clockwise direction will be taken as a negative direction because theta will decrease. So because we are in a circular path, when you're moving, the radius is going to remain the constant. The radius, it says radius is rho, so the radius rho is going to be a constant. So only thing that is going to change is theta as you move along this path. So theta is a very good choice for the parameter over here. Okay, so here z is can be written because rho is the radius, so rho, and because theta is a parent rho, we can write this in the Euler's notation. So e to the power I theta, we write z as z equal to rho e to the power I theta. Okay, which implies z is a function of theta. Okay, z is a function of theta, rho e to the power rho e to the power I theta. Okay, so once you have figured out, so this, that means we are parameterizing the curve. Remember, the parameterization depends only on the curve. Okay, parameterization does not depend on the function, it depends on the curve. So the parameterization of z with respect to theta. So here we are doing a parameterization of z with respect to theta. All right, so next thing that we need to do is, if you look at the formula, let me grab the formula also from here. The expression is, sorry, okay, so this is the formula that we're going to use to evaluate this integral. So this is the formula. So in this formula, what we need z dot also. That is a derivative. So here now, what is the derivative? That is z dot of theta. T is theta. What is the derivative? What will happen if you differentiate this? Z is equal to rho e to the power I theta. So what is the derivative of z with respect to theta? Z dot is dz by d theta. Dz by d theta. Can anyone tell me what will this be equal to? Differentiate z.
Rho I e to the power I theta.
That's it, right? So it will be simply that I is going to come here. So it is going to be equal to I into rho into e to the power I theta. Okay, so this is your z dot. Okay, so we found out what is this z dot. Now all we need to do is just substitute everywhere, wherever in this function. Okay, so what is f of z? Given f of z is equal to, as per this problem, f of z is equal to z to the power n. Okay, so therefore in this problem we need the second part, that is there is a first part, f of z of t. What will this be equal to? Very simple. In this function, wherever there is z, you replace it with this one. It's parameterized representation. So z is rho e to the power I theta whole to the power n. So this is going to be equal to rho to the power n e to the power I n theta. Okay, so this is this part. Okay, this is this part. So now we can just we can go ahead and integrate this. Okay, integrating over c. Okay, let me just write down one more thing. Also, what is c? What is c? C is a curve. It's a circle, no? It's a circle of radius rho in the complex plane. So c is the curve. This curve c is a circle of radius rho. Circle of radius rho. Okay, it's a circle of radius rho. Just give me a second. I'm getting a phone call. Just hold on. Okay. Yeah. So sorry for the interruption. Okay. Let's get back here. All right. So here C is a circle of radius rho. So C is a circle of radius rho. So if C is a circle of radius rho, that means we're integrating over one full cycle. Okay. So this implies that this theta that we have here, okay, this theta that we have chosen, the parameter theta that we have chosen, what will be the range of values that it will take? The range of values that it will take, its smallest value, let's say it starts from here. Let's say you start from this point. Okay, let's say you start from this point, go all the way and come back here. That means your starting point is 0. Okay, and you come back after one full cycle. You just come back. You come back means you're completing one full cycle. That's going to be 2 pi radians. Okay, so this implies this lower limit that we have here, this lower limit a is going to be 0, and this upper limit that we have here, the upper limit b, this is going to be equal to twice pi. Is that understood? So we have everything in place here. We need to integrate this. We have everything in place. We know what is f of z of t. We know what is z naught of t, z dot of t, and we have a and b over here, right? All we need to do is just substitute everything here. So therefore, the integration over c of z to the power n into dz, the integration over c of z to the power n, this will be equal to, just make all the substitutions. There is a here. Okay, lower limit is a is 0 here, upper limit is b here is 2 pi. Make the substitutions. Next, what do we have? F of z of t. F of z of t is this rho to the power n. F of z of t is rho to the power n into e to the power I into n into theta. theta. Okay, and z dot is this, which is I into rho into e to the power I theta. Okay, so this is what we have. All right, and then dt means d theta. So this is what we need to evaluate. This is much easier to evaluate. Okay, that's what we see here. So first thing is the constants we will just take outside. So I is a constant which will come outside. Then rho to the power n is there and rho is there. So that was rho to the power n plus 1, rho to the power n plus 1, and what is left behind is 0 to twice pi, 0 to twice pi e to the power I, there is n theta and theta, so this will become n plus 1 theta into d theta. So far so good, everyone? All of you, is this clear so far?
Yes, sir.
Everybody?
Yes, sir.
Okay.
Yes, sir.
All right. So now let's say there are two possibilities here. If you look at this one, there are two possibilities here. First possibility is if n is equal to -1. Okay. If n is equal to -1, then what will happen? That is n is equal to -1. That is 1 by z. Okay. N is equal to -1. That is you are trying to integrate. Okay. This is a closed loop. We have to give us put a circle here. We're trying to integrate this. N is equal to -1, z to the power -1 is dz by z, dz by z. Okay. So in this case, what will happen? Okay. In this case, what will happen? What will happen is basically this. So C, left hand side, will write it as it is, z to the power n dz. This is equal to I rho n is equal to -1 plus 1. Okay, n is equal to -1 plus 1. Then integration 0 to 2 pi e to the power I into -1 plus 1 into d theta. Okay, so this is going to give us, this is rho to the power 0, which is equal to 1. So I integration from 0 to twice pi e to the power, this is anyway, this is also going to be 0, e to the power 0, which is into d theta. This is equal to I into integration from 0 to twice pi. This e to the power 0 is anyway 1. So we have what is left is d theta. So integration of d theta is nothing but theta. So I into theta. Lower limit is 0, upper limit is twice pi, which is I into upper limit minus the lower limit. So this is going to give us the value twice pi I. Okay, it's going to give us a value 2 into pi into I. So if n is equal to -1, if n is equal to -1, this integral, this function that we are trying to integrate, that one's value is going to be equal to twice pi I. Okay, but what if n is not equal to -1? That case, what will happen? If n is not equal to -1, then what will happen? Let's see. Let's look at only the integrand. Okay, what is the integrand? The integrand is e to the power I n plus 1 theta. Okay, if n is equal to not equal to -1, the integrand is the integrand here, that becomes e to the power I n plus 1 into theta. Okay, this is the integrand, and this integrand you can simply write this, because you can use the Euler's notation. So this is going to be equal to cos of n plus 1 into theta plus I into sine of n plus 1 into theta. So therefore, when we try to integrate this now, integration over C, z to the power n into dz, for this case, this is going to become Okay, this is going to become I into rho to the power n plus 1, I into rho to the power n plus 1, and then we have two integrals, one is this cos, another one is psi, another one is sine. So 0 to 2 pi cos of n plus 1 theta into d theta. This is one integral, and the other integral will be equal to I into integration from 0 to twice pi sine of n plus 1 theta into d theta. Now what will these be equal to? What will be this result? What will be this result? Both of these integrals will turn to be 0. Why is it 0? Can anyone tell me? Why are they 0? Both of them? Can anybody tell me? Because sine and cos, no? Sine and cos. It's a integral multiple of sine and cos. That means we have integral multiple cycles, right? Integral number of cycles of sine and cos. Sine and cos integration over one full cycle, how much is that? It's 0, no? Sine function and cos function, if you integrate over integral multiples, that means over one full cycle, two full cycles, three full cycles, n number of full cycles, or n plus one number of full cycles, if you integrate, the result will always be 0. Yes or no?
Yes, sir.
So
Yes,
for
sir.
that reason, both of them will be 0. So because this is 0, so overall this also is going to be 0. Okay, so we can write down the answer like this. So therefore, we can say that this integration that we are trying to perform, the integration over C of z to the power n dz, okay, this will have two possible values. One value will be twice pi I. One value is twice pi I. This is if n equals minus 1. And the other one is 0. This is if n is not equal to minus 1. For any other value of n, this will be non-zero. So this is the result. Okay. Hence, because if it is minus 1, so we get this very useful result. The result is the closed loop integral of dz by z. The closed loop integral of dz by z, it is always equal to twice pi I. It is always a constant. It's always equal to twice pi I. And this one, okay, this result, okay, we can have a shift of the coordinates. So with a coordinate shift, with a coordinate shift, that is this C, it's a cycle which whose center is at 0. Instead of the center being at 0, let's say you shift the center to some other point, then and you then perform the integration. Okay, so the curve C, and then you perform the integration over some other center, that is z minus z naught. This result also will be in general equal to twice pi I. Okay, so that's basically how you can solve this. So using parameterization, okay, this is the result using parameterization. So you can try this other problem. Okay, okay, I think there's something missing here. You real part and imaginary part over to, okay, I'll give you the two parts. Okay, I'll give you two different parts. Let me just quickly grab this. Okay, the two parts are this. So we have 2 points. So 0, so first point, and the other point is 1 plus twice I. So let's say this is 1, this is 2, this is the real part, and this is the imaginary part of Z. So this is 1, this is 2, this is I, and this is twice I. So I and twice I. So the final point will be this one. Okay, this is 0 and this is 1 plus twice I. So there are two paths. One path is the direct path. One is you could take the path directly from this point to this point, and the other path is you could go like this. Let me make it a little thicker. This is one path. Okay, and the other path is you could start from here, go till here, and from here go all the way up till here. So these are the two paths. Path number 1, this is the first path, and this is the second path. Okay, so integrate this over these two different paths. So here you'll have to actually find a way, find some kind of a parameter which is going to represent this. So please try this. Okay, please try to work this out at home. Okay, you can discuss among yourself, and if you have any queries you can ask me also. Just feel free to ask me. It's 1:43. I just have 2 more minutes left, so I think I'm going to stop here. In the next class I'll do this ML inequality part in the next class, that is tomorrow. So do you all have any questions so far? Any questions? Anybody?